The night sky is filled with points of light that seem close, but are separated by distances so vast that they might as well be worlds apart. Among these distant stars, galaxies and the empty space between them, exist mysteries that humans have only begun to explore. What really lies out there in the darkness? Is space simply empty? Could there be places where time itself slows down, or where entire galaxies hide, unseen by our telescopes? Some say that hidden forces, bizarre objects, and even so-called cosmic echoes fill this vast space. Let's venture through the endless possibilities of the universe, exploring the strangest, most mind-bending ideas about space. Galactic skeletons, the remains of stars long gone. Scattered across the vastness of space, there are places where stars once lived and shined, only to end in fiery explosions that marked their death. These regions are filled with galactic skeletons, the remnants of stars that lived long ago and exploded in supernovae. These stellar remains shape the galaxy, creating the materials that become the next generation of stars, planets, and possibly even life itself. When a massive star reaches the end of its life, it has burned through its fuel and can no longer hold back the intense forces within. The result is a supernova, a powerful explosion that blasts the star's outer layers into space. This explosion creates a cloud of gas and dust stretching across light years, called a nebula. These nebulae are some of the most striking and colorful formations in the universe, illuminated by the energy from the explosion and the lingering radiation left behind. The explosion releases elements like carbon, oxygen, nitrogen, and iron, materials that the star had forged in its core over millions of years. These elements are the building blocks of life, essential for planets, plants, animals, and people. In this way, supernovae serve as cosmic recyclers, taking the materials from one generation of stars and scattering them across space to form the next. In some cases, the nebula left behind from a supernova will collapse under its own gravity, forming a new star. This process of rebirth can take millions of years, as clouds of gas and dust slowly come together, spinning and heating until a new star ignites. This recycling of materials from dead stars to form new ones creates a continuous cycle of life and death in the galaxy, a vast rhythm that stretches back to the very first stars. Our own Sun and our solar system are thought to have formed from a similar stellar nursery billions of years ago. We are, in a very real sense, made of the remains of stars that once exploded. In the galaxy, supernova remnants come in many forms. Some are vast circular clouds, like the famous Crab Nebula, which continues to expand at incredible speeds. Others are more chaotic and irregular, with tangled clouds of dust and gas spreading across light years. These shapes depend on the original size of the star, the power of the explosion, and the environment around the star. If a supernova occurs near other stars or nebulae, it can create a more complex formation, with the explosion sending ripples through nearby gas clouds. The shock waves can compress nearby gas clouds, pushing them together and kickstarting the process of star formation. Sometimes, this chain reaction of star formation can create entire clusters of new stars, all formed from the shock waves of a single supernova. After the star explodes, its core can collapse into an incredibly dense object called a neutron star, a remnant so compact that a single teaspoon would weigh billions of tons. Neutron stars are some of the most extreme objects in the universe, with powerful magnetic fields and rapid spins. Some neutron stars emit beams of radiation as they rotate, creating a lighthouse effect that can be seen from Earth as a pulsing light. These are known as pulsars, and they are among the most precise clocks in the universe, with some rotating hundreds of times per second. Another possible outcome of a supernova is the formation of a black hole. When the core of a star is even more massive, the collapse doesn't stop at a neutron star. It continues until it becomes a point of infinite density, a black hole. These invisible remnants of massive stars lurk in the galaxy, shaping the space around them, pulling in gas and dust, and sometimes merging with other black holes. Without supernovae, the galaxy would be a very different place, filled with stars but lacking the rich variety of elements needed for planets like Earth. These stellar skeletons are the seeds of the cosmos, the essential ingredients that allow for the complexity and diversity of the universe we see today. The cosmic mirage. Are we seeing real stars or their ghosts? Light is fast. It moves at nearly 300,000 kilometers per second, making it the fastest thing in the universe. But even at this incredible speed, it takes time to travel across the enormous distances of space. Light from the sun, for instance, takes just over 8 minutes to reach Earth. So we're always seeing the sun as it was 8 minutes ago. But when we look at stars farther out, the delay grows longer. The light from Proxima Centauri, our closest stellar neighbor, takes more than 4 years to get here. For other stars, the delay is hundreds, thousands, or even millions of years. This means that when we gaze into the night sky, we're looking back in time. Imagine looking at a star that is 10,000 light-years away. The light we're seeing now left that star all those years ago, before recorded human history began. For all we know, the star could have gone supernova centuries ago. What we see is not the star's present state, but a snapshot from its past, a distant echo carried across space. In this way, every star we see is part of a cosmic record, a kind of archive that preserves the history of the universe. Light itself acts like a storyteller, carrying news from distant realms, but always delayed by the vast distances it has to cross. This delay is especially dramatic for galaxies and stars billions of light-years away. When we look at the farthest objects in the universe, we're not just looking back hundreds or thousands of years, we're looking billions of years into the past. The James Webb Space Telescope, for example, has captured images of galaxies so far away that the light left them over 13 billion years ago, shortly after the Big Bang. We see these galaxies as they were in the earliest days of the universe, glimpsing a time when stars were first forming, a time of cosmic birth and creation. For scientists, this delay in light offers a unique opportunity. Observing distant stars and galaxies allows us to study the universe's history, to understand what it looked like at different stages. By looking farther and farther away, astronomers can construct a timeline of cosmic events, tracing the formation and evolution of stars, galaxies, and even the universe itself. The farther we look, the deeper we see into the past. The effect of distance on light also means that we can't always be sure of what's happening in real time in faraway parts of the universe. If a major event, like a supernova or the formation of a new galaxy, occurred hundreds of thousands of light-years away, it would take just as long for us to know about it. In essence, the universe is always revealing its story to us, but only bit by bit, like turning the pages of an old book one at a time. In some cases, the light from a star can bounce off nearby clouds of gas or dust, creating a delayed reflection that continues to travel through space. These light echoes allow us to observe events that happened in the past more than once, as the reflected light reaches us on a delayed schedule. For instance, if a star goes supernova, its light might reach us directly, and then, years later, we might see the same event again as light reflects off a distant cloud. The abyss's breath, strange, soundless currents in space. In the vastness of space, where emptiness seems to stretch on forever, there are strange and silent forces moving in ways that we are only beginning to understand. Unlike the oceans on Earth, with their visible currents and waves, space appears empty and still, without movement or sound. But even in these seemingly silent areas of the universe, energy flows, creating invisible patterns that shape the cosmos in ways we might not expect. These mysterious flows, like cosmic currents, drift through space, their presence sensed by the effects they leave behind rather than by any visible motion. Space itself is not a perfect vacuum. It holds a delicate scattering of particles, fields, and forces that connect galaxies and clusters like an unseen web. These currents move through something we call the cosmic medium, which includes a sparse mix of gas, dark matter, and magnetic fields. The cosmic medium is so thin that it seems like pure emptiness. But these scattered particles and forces form a kind of framework that binds galaxies into groups and clusters and stretches for billions of light years. And within this cosmic framework, subtle flows of energy move across unimaginable distances. One of the ways scientists detect these strange currents is by observing how galaxies and clusters drift through space. This motion, often called peculiar velocity, is a way of measuring movement that doesn't fit the regular expansion of the universe. Galaxies seem to drift in certain directions, influenced by the subtle push and pull of invisible forces. This flow of galaxies hints at unseen structures, where the fabric of space itself seems to have currents that guide galaxies along certain paths. These motions aren't fast by any measure, they unfold slowly over millions and billions of years, but their effects shape the universe on the largest scales. Cosmic currents are driven by gravity and dark matter, which create vast regions of attraction and repulsion. Gravity pulls matter together, forming galaxies and clusters, while dark matter, an invisible type of matter, adds an extra gravitational influence, pulling galaxies into cosmic structures. Over time, these forces shape paths, guiding clusters and galaxies to drift along invisible currents. Imagine a leaf floating slowly on a gentle river, pulled along by currents we can't see. Similarly, galaxies follow the flows created by gravitational fields in the vast cosmic sea. One example of this flow is something known as the Great Attractor. Discovered in the 1980s, the Great Attractor is a mysterious region in space where hundreds of galaxies, including our own, are being pulled towards. The pull of this region is so strong that it influences galaxy clusters millions of light years away. And yet, scientists can't clearly see what's causing this attraction, as the area is obscured by our own galaxy. The Great Attractor is thought to be a large concentration of matter, perhaps a supercluster of galaxies or an enormous concentration of dark matter. This massive structure seems to act like a cosmic whirlpool, pulling galaxies in its direction. Between galaxies lie immense empty regions called cosmic voids, vast stretches where few galaxies exist. Surrounding these voids are filaments, long, thin strings of galaxies, and clusters that form a web-like structure. Scientists call this pattern the cosmic web. This web is shaped by the slow and steady flow of matter across the universe, creating dense regions where galaxies cluster together, as well as empty regions, where cosmic currents flow through mostly empty space. The cosmic web is like a frozen ocean, with currents and waves that have settled over billions of years, forming a pattern that stretches across the universe. The cosmic microwave background radiation, or CMB, is the faint glow left over from the Big Bang, filling every part of space with a soft, steady light. But this light isn't perfectly uniform. It has slight variations, or hot and cold spots, that trace the first clumps of matter that would eventually form stars and galaxies. These tiny fluctuations are believed to be the initial ripples, the earliest currents in the fabric of space. Over time, gravity has amplified these tiny variations, forming currents of matter that slowly gathered into galaxies and clusters. In space, magnetic fields stretch across vast distances, often linking galaxies in ways that aren't immediately visible. Scientists believe that these magnetic fields can influence the motion of charged particles, like cosmic rays, which flow along these fields in huge loops and arcs. These particles create additional, smaller currents within the larger flows of galaxies and clusters. Over time, these magnetic fields may help direct the movement of particles across the cosmos, creating streams of energy that subtly shape the paths of stars, dust, and gas in space. To study these silent flows, scientists use simulations and models, creating computer-generated versions of the universe. By simulating the effects of gravity, dark matter, and dark energy, they can observe how galaxies and clusters should move over billions of years. These simulations have revealed unexpected patterns in cosmic flows, showing that some galaxies appear to follow streams that stretch for hundreds of millions of light years. These models help scientists understand how the universe evolved and how the cosmic web took shape. But they're still only approximations, clues that hint at forces we can barely comprehend. Quantum dreams. Could the universe be imagining itself? What if, at the smallest, most fundamental level, the universe is not just a place where things happen, but a vast network that generates reality through its own awareness of itself? To even begin to understand this idea, we have to look to quantum mechanics, the branch of physics that studies particles at the smallest scales. Quantum mechanics reveals a world where particles don't follow straightforward paths or behave predictably. Instead, particles like electrons seem to exist in many places at once, in a kind of cloud of possibilities. Only when we measure or observe them does their position become fixed, as if the act of observing helps decide where they are. It's as if particles exist in a state of potential rather than in a solid, fixed form. Some scientists and thinkers have proposed that this act of observing, this collapse of possibilities into a single reality, suggests that the universe itself might have a way of observing itself, creating reality as it interacts with itself. In this view, the universe is a kind of self-sustaining loop, where each particle, each force, each moment is connected in such a way that the cosmos maintains its own existence. This idea draws from a concept known as the self-simulation hypothesis. According to this hypothesis, the universe could be like a vast computer, constantly running a kind of simulation of itself. Just as a computer program relies on code to create virtual worlds, the universe might use its own laws of physics to generate the reality we experience. In a self-simulating universe, every interaction, every force, every particle might be part of a grand, self-contained system that endlessly calculates itself. In a way, this hypothesis is like a modern twist on ancient philosophical questions about reality. Philosophers have long wondered if the universe has some form of consciousness, or if reality is an illusion created by our minds. The self-simulation idea suggests that the universe might indeed be a kind of consciousness, not a conscious being in the way we think of humans or animals, but a system that generates awareness through its own structure. If the universe is self-simulating, could it be creating smaller pockets of awareness within itself? Could human consciousness be a natural result of the universe's self-creating process, like sparks that emerge from a fire? The self-simulation idea suggests that consciousness might be an inevitable part of the universe's structure, something that emerges as part of the cosmic program. In this view, life and consciousness are not accidents or isolated events. They're part of the universe's own self-understanding. Some scientists believe that this self-sustaining universe could help explain why physical laws appear so perfectly fine-tuned for life. In a self-simulating universe, physical laws might not be set in stone. They might be flexible, adjusting over time to create stable environments where consciousness and life can develop. This concept, known as self-organized criticality, suggests that complex systems naturally evolve toward balance. If the universe is indeed self-simulating, then perhaps it naturally adjusts itself to maintain conditions that allow consciousness to arise. This would mean that life is not a rare accident, but an essential part of the universe's own self-sustaining process. Forgotten suns, stars that exist beyond the observable universe. Beyond the reach of our most powerful telescopes and the limits of our observable universe, there may lie countless stars, galaxies, and clusters we will never see. These distant, unreachable suns, separated by an expanse of space so vast it defies comprehension, are hidden from us by the very nature of the universe's structure. They are beyond what scientists call the cosmic horizon, a boundary defined by how far light has traveled since the beginning of time. The cosmic horizon is like an invisible wall. It marks the limit of how far we can observe because light from beyond this point has not yet had time to reach us. The universe is around 13.8 billion years old, which means that light from regions farther than that hasn't had a chance to cross the vast distances to Earth. This doesn't mean those stars and galaxies don't exist. It just means they're too far for us to see or detect in any way. These forgotten suns, the stars beyond our cosmic horizon, are a mystery in every sense. They might look similar to the stars we see in our skies, or they might be entirely different, shaped by environments and conditions unlike anything we've encountered. With no way to observe them directly, we can only imagine what they might be like. They could exist in clusters and galaxies that mirror the ones we know, following similar laws of physics, forming and burning and dying just as the stars near us do. Or they could exist in parts of the universe with subtle variations in the physical laws we understand. Over time, galaxies and stars are moving farther apart, pulled by a force known as dark energy. This expansion is not like a simple explosion. It's a stretching of space itself, which means that over billions of years, regions of the universe are being pushed farther and farther away from each other. Eventually, the expansion will carry distant stars and galaxies out of sight, pushing them beyond the cosmic horizon. Once this happens, their light will never reach us, and they will essentially disappear from our observable universe, even though they continue to exist. The laws of physics we know, such as gravity, electromagnetism, and the nuclear forces that power stars, seem to apply consistently throughout the observable universe. But beyond our cosmic horizon, it's possible that conditions might be slightly different. Some scientists suggest that in these hidden regions, variations in physical laws could exist. This doesn't mean stars beyond the horizon defy gravity or stop shining. It just means they could follow variations of the rules we know, shaped by the unique circumstances of their surroundings. Could there be suns larger, hotter, or stranger than any we have discovered? Could they form in ways that are impossible under the conditions within our observable universe? Perhaps there are entire clusters of stars that burn in colors we cannot imagine, or supernovas that explode in ways that defy our understanding. Without the ability to observe these distant suns, we can only speculate. They might host planets and solar systems that follow patterns we would find strange or unpredictable, shaped by subtle differences in cosmic conditions we are unable to see. Another possibility is that these unreachable stars could be shaped by different forms of dark matter or dark energy. If dark matter behaves differently, perhaps it would create galaxies and star clusters with unique shapes and formations. If dark energy were weaker or stronger, it could change how stars are born or how long they live, resulting in suns that last far longer or burn out more quickly than any we have observed. Some scientists wonder if one day new discoveries might allow us to understand what lies beyond our observational limits. Perhaps there are faint traces, signals, or effects that we might detect, giving us clues about these distant regions. But for now, these stars remain hidden, lost in a vast, silent expanse. Where time warps, strange regions that twist and slow reality. In the vast fabric of the universe, there are places where time itself behaves in ways we don't expect. These regions, often near massive objects like black holes or dense clusters of matter, seem to slow time down, stretching moments into long, strange sequences. Time becomes something malleable, something that twists and bends in response to the powerful gravitational forces around it. This bending of time is a result of a phenomenon called gravitational time dilation. According to Einstein's theory of general relativity, time isn't a steady, unchanging flow. It's something that can be stretched or compressed, depending on the forces around it. The closer you get to a massive object, the stronger the gravitational pull, and the slower time moves in that area. It's as if gravity holds time in place, anchoring it in a way that makes it pass more slowly. For someone far from the gravitational pull, time flows normally, but for someone close to a massive object, time seems to creep along. Black holes are perhaps the most dramatic example of this time-warping effect. A black hole's gravity is so intense that not even light can escape it, and as you get closer to its edge or event horizon, time slows down almost to a standstill. If an astronaut were to approach a black hole, observers from a distance would see their movements slow down more and more until it seemed as if they were frozen in time at the event horizon. For the astronaut, however, time would feel normal. Even as they drifted toward the center of the black hole, they wouldn't feel time slowing down at all. Because light takes time to travel, the light from distant stars and galaxies we see today left its source millions or even billions of years ago. If we could place an observer near a black hole, where time moves slowly, they might see events in the universe unfold at a much faster pace, almost like watching a film on fast forward. This means that while they're experiencing only a few moments, whole epochs could be passing in the wider universe. In these zones of extreme gravity, space itself is also bent and twisted. A phenomenon known as space-time curvature occurs near massive objects, causing both space and time to be pulled inward, like a fabric stretched by a heavy weight. In such regions, distances can be distorted, making paths appear curved rather than straight. This bending of space has been observed around stars, planets, and even galaxies, where the light from objects behind them appears warped, creating an effect known as gravitational lensing. It's a strange trick of nature. When light from a distant star or galaxy passes near a massive object on its way to Earth, it bends, creating an almost magnifying effect that allows us to see objects far beyond our usual reach. Gravitational lensing doesn't just warp light, it warps time as well. When light travels near a massive object, it takes a longer, curved path, stretching out the time it takes to reach us. For astronomers, this phenomenon is like a natural time machine. By studying these stretched-out beams of light, scientists can glimpse events that happened eons ago. Entire galaxies, clusters of stars, and even the faint glow of the early universe can appear in these distorted images. Through gravitational lensing, we can observe light that has traveled across billions of years, allowing us to look back to some of the earliest moments after the Big Bang. Not all regions with warped time are near black holes. Time dilation also occurs around other extremely massive structures, like galaxy clusters. These clusters are collections of thousands of galaxies bound together by gravity, creating regions of immense mass and, consequently, strong gravitational pull. Time moves slower within these dense clusters than it does in the emptier regions of space. To an outside observer, events within the cluster would appear to move at a slightly slower pace. The sheer mass of these clusters pulls on the fabric of space-time, causing both time and space to bend around them. Starless wonders, massive objects that never became stars. In the cosmos, not every large body with star potential bursts into life. Some remain in a quiet, unlit state, floating through the galaxy as enormous but dark objects. These failed stars, also known as brown dwarfs, form when massive clouds of gas and dust collapse under their own gravity. Yet, despite their size, these objects don't have enough mass to sustain the nuclear fusion that powers stars. Without fusion, they don't light up the way stars do, and instead, they drift as cool, dim bodies in space. Brown dwarfs are a curious in-between in the universe. They're much larger than planets, sometimes dozens of times the mass of Jupiter, but they lack the critical mass to reach the fusion threshold that transforms a body into a true star. A star like our Sun shines because the extreme pressure and heat at its core fuse hydrogen atoms together, releasing enormous amounts of energy in the form of light and heat. Brown dwarfs, however, fall just short of this mark. They may reach impressive sizes, but without enough mass, the pressure and temperature at their cores never climb high enough to sustain fusion. They're not easy to spot because they emit very little light, only faint glows in infrared wavelengths, the heat left over from their formation. Unlike stars, which stand out brightly against the dark background of space, brown dwarfs are nearly invisible. Most were discovered using infrared telescopes, which can pick up the faint heat signatures of these dim bodies. Even now, scientists estimate that we've only located a fraction of the brown dwarfs drifting in our galaxy. The story of a brown dwarf's formation begins much like the birth of a star. A cloud of gas and dust collapses, pulled together by gravity. As the particles clump together, the mass grows, and with it, the pressure and temperature at the center. But for brown dwarfs, there's a limit to how far this process can go. If the mass isn't quite enough, the core won't reach the millions of degrees needed to kickstart hydrogen fusion. Instead, the object stabilizes as a brown dwarf, radiating only a faint warmth as it slowly cools over billions of years. Brown dwarfs come in a range of sizes and temperatures, with some on the borderline between planets and stars. Scientists have found brown dwarfs that are as small as a few times the mass of Jupiter and others approaching the lower mass limit for stars. Some brown dwarfs even have their own planetary systems, orbiting planets that were pulled into their gravity, forming small, dark solar systems that drift through the galaxy like invisible islands. Although they don't have the power of stars, they aren't entirely inactive. They have a brief period of activity in their early lives as they continue to contract and generate heat. For a short time, they can fuse deuterium, a heavy form of hydrogen that requires less pressure and temperature than standard hydrogen fusion. This brief fusion phase produces some warmth, but it's not enough to light them up like stars. Eventually, they exhaust their deuterium supply, leaving them to cool quietly in the darkness. The rarity of brown dwarfs in our galaxy is a puzzle to astronomers. There are far fewer of them than we might expect, given how often clouds of gas and dust collapse. Some scientists suggest that brown dwarfs are hard to find because they're so dim, and we might simply be missing many of them. Others think that conditions for forming brown dwarfs are specific, requiring a certain balance in the cloud's density and temperature. Without the right conditions, a collapsing cloud either fails to form a body or gathers enough mass to become a full-fledged star, skipping the brown dwarf stage altogether. While brown dwarfs don't shine like stars, they do interact with their surroundings in interesting ways. They have magnetic fields, and some even produce flares, small bursts of energy similar to the flares that erupt on the surface of our Sun. These flares release particles and heat, briefly lighting up the brown dwarf's atmosphere. Although they're dim and cold compared to stars, brown dwarfs can have turbulent weather patterns, driven by convection currents in their atmospheres. These currents stir up gases, creating swirling clouds and bands similar to those seen on planets like Jupiter. Because they don't burn as hot as stars, brown dwarfs have more complex atmospheres, with molecules like methane, water vapor, and even clouds of minerals that condense in the cold upper layers. In some ways, brown dwarfs resemble giant gas planets with thick, stormy atmospheres full of exotic compounds. They're a window into the kind of chemical processes that can occur in cool, dense atmospheres, different from the intense heat and radiation of stars. Some scientists think just as planets form around stars, small bodies might form around brown dwarfs, creating miniature systems in the darkness. If so, brown dwarfs could represent a unique type of environment where planets orbit a body that gives off little heat or light. In recent years, scientists have even found evidence of brown dwarfs that seem to orbit other stars, much like planets. These rogue brown dwarfs are drifters that likely formed far from their parent stars and were captured by their gravity later. Suspended between universes. Could some planets exist in two realms? Imagine a planet, far out in the reaches of space, which feels the gravitational tug of not just one universe, but two. Suspended between realms, such a planet might be subjected to forces pushing and pulling it in ways unlike anything we see in our familiar universe. If our universe is part of a larger multiverse of other universes, these neighboring universes might float like bubbles in a larger cosmic sea, brushing up against one another from time to time. In these areas where two universes might touch or overlap, strange effects could occur, including the possibility of a planet that feels the gravitational influence of two realms. One of the concepts supporting this idea comes from string theory, an area of physics that suggests that all particles and forces are made of tiny vibrating strings, which exist in many dimensions beyond the three we're familiar with. These extra dimensions might be hidden from our view, compacted so tightly that we don't directly see them. But in regions where two universes come close, some of these hidden dimensions might become accessible, allowing for gravitational forces to leak from one universe to another. A planet caught between two universes would likely experience odd, shifting gravitational forces. In our universe, planets orbit stars in predictable paths, held in place by the balance between their forward motion and the pull of gravity. But if an unseen force from another universe was pulling on a planet, it could disrupt this balance. The planet's orbit might be unstable, wobbling or drifting in unpredictable ways. From our perspective, it would look as though an invisible force was tugging on the planet, shifting its path without any clear explanation. If it were exposed to forces from another universe with different physical laws, its surface might behave differently from other planets. The materials that make up its crust, mantle, or core could respond to these forces in unpredictable ways. The gravity on this planet might be stronger or weaker than expected, and its atmosphere could be affected by the energy crossing between realms. Its landscape could be shaped by interactions that seem impossible to us, areas where the ground warps or where time itself behaves strangely. Could a planet like this act as a kind of gateway between universes? If two universes were close enough for a planet to be influenced by both, it raises the question of whether matter or energy could move between them. In theory, if gravitational forces can cross between universes, perhaps other forces, like electromagnetic radiation or even particles, could make the leap as well. This planet, suspended between realms, might experience strange flashes of light or bursts of energy that seem to come from nowhere, signs of forces slipping through from the other universe. If we were able to observe such a planet, it could give us a unique view into the multiverse, allowing us to detect the presence of another realm through its effects. Scientists are constantly searching for signs of other universes, but because they exist outside our observable universe, they're incredibly difficult to detect directly. A planet affected by forces from another universe could be like a window into that hidden realm, providing hints of what lies beyond our own cosmic horizon. The idea of interdimensional planets is speculative, but there are a few clues that suggest our universe might interact with others in subtle ways. Some physicists propose that certain gravitational anomalies we observe, like the unexpected motion of some galaxies, could be hints of forces from other universes. If galaxies are influenced by unseen gravitational forces, it's possible that individual planets or star systems could be similarly affected. For scientists studying the multiverse, an interdimensional planet would be an incredible discovery, a rare chance to study the boundary between realms. Observing a planet like this would help scientists understand the fundamental structure of reality itself. The silent quake. Do unseen forces ripple through space? In the vastness of space, some scientists believe there are silent, invisible quakes, ripples moving through the fabric of the cosmos, hinting at massive unseen events or objects too far or too faint to detect directly. Unlike earthquakes, which send waves of energy through the ground, these cosmic quakes travel through the very structure of space itself, bending and stretching it as they pass. We know about these space-rippling phenomena because of gravitational waves, faint distortions in space-time that were first theorized by Einstein. In recent years, scientists have finally captured evidence of these waves, confirming that space can indeed ripple. But these are just the beginning. There may be other, deeper quakes out there, quiet signals of forces or events hidden beyond the limits of our observation. Gravitational waves are like ripples on the surface of a pond, caused by massive events such as the collision of black holes or neutron stars. When two enormous objects collide, their energy warps space and time, sending out waves that travel across the universe. By the time they reach Earth, these waves are incredibly faint, but they stretch and compress the space they pass through, even if just by a tiny fraction. Special detectors like LIGO and Virgo are able to sense these minute changes, allowing scientists to hear the distant echoes of these cosmic events. These gravitational waves tell us about massive collisions billions of light years away, events so intense that they send out tremors across the universe. But some researchers wonder if there are other kinds of quakes rippling through space, disturbances caused by things we haven't even discovered yet. There are still many unexplained phenomena in the universe, forces that seem to operate without any visible cause, and patterns in the structure of the cosmos that seem to defy explanation. Could these be signs of hidden forces at work, sending out waves we can't yet detect? It's possible that, like gravitational waves, these silent quakes are caused by massive events, but ones that don't produce light or detectable energy in ways we currently understand. The search for silent quakes is a difficult one. Unlike gravitational waves, which can be detected by measuring the minute stretching and compressing of space, these quakes might be far subtler, creating shifts that are almost impossible to measure. However, scientists are developing new techniques to study large-scale cosmic structures in greater detail, hoping to find clues that might reveal the presence of these hidden forces. By observing the motion of galaxies over time, researchers can look for patterns that might indicate the influence of unseen quakes. Some astronomers are studying the distribution of galaxies across the universe, mapping out the cosmic web. As scientists study this structure, they occasionally notice unusual patterns, flows of galaxies moving in the same direction, or clusters that seem to shift unexpectedly. These patterns could be signs of silent quakes, waves moving through the cosmic web, affecting galaxies on an enormous scale. Black hole seeds are dark voids, breeding grounds for black holes. Black holes are usually associated with the collapse of massive stars, dense with matter and energy. But there's a growing curiosity around whether black holes can form in a different way, in regions where typical cosmic processes don't happen. Places where the usual ingredients for black hole formation are missing. Could it be possible that these dark voids are quiet breeding grounds for black holes, formed not from collapsing stars, but from other processes? Scientists have long known that black holes can form when massive stars reach the end of their lives. When these stars burn through all their fuel, they collapse under their own gravity, compressing into a single point with an intense gravitational pull. This point, known as a singularity, becomes a black hole, a region of space where gravity is so strong that not even light can escape. But what if black holes could form without the need for stars at all? At the quantum level, space isn't empty. Even in regions that appear devoid of matter, space is never truly still. Tiny particles flicker into existence and then vanish again in fractions of a second. These are known as quantum fluctuations. Under normal circumstances, these particles are too small and too short-lived to have any lasting impact. But some scientists theorize that if certain conditions are met, these fluctuations could gather enough energy to create a small, dense region of space. Over time, this dense region could accumulate more mass and eventually form a black hole, growing slowly in the emptiness of the void. These black holes, formed from quantum seeds rather than collapsing stars, would likely start out extremely small, perhaps only the size of an atom. Unlike stellar black holes, which can form in seconds during a star's collapse, black holes in voids would grow very gradually, gathering stray particles over millions or even billions of years. In these empty stretches of space, particles and energy are rare, so the growth of a black hole would be painstakingly slow. Yet with enough time, these seed black holes could become substantial, even powerful objects in the cosmos. There is also the possibility that these black hole seeds could have formed very early in the history of the universe, when conditions were vastly different. Shortly after the Big Bang, the universe was filled with a hot, dense soup of particles and energy. As it expanded and cooled, tiny fluctuations in this early cosmic soup could have created regions of slightly higher density. In some cases, These regions might have been dense enough to collapse into black holes, forming what scientists call primordial black holes. Unlike black holes formed by stars, primordial black holes would have emerged in the early moments of the universe from the very fabric of space itself. Some of these black holes might have evaporated over time, while others could still be drifting through space, hidden in the dark regions between galaxies. If they're out there, they could serve as tiny windows into the conditions of the early universe, showing us what space was like before stars and galaxies formed. The memory of light. Can photons remember their journey? In the strange world of quantum mechanics, light behaves in ways that challenge our everyday understanding. Photons, the tiny particles that make up light, travel across unimaginable distances, moving from stars to planets and beyond, carrying energy with them as they go. These particles may be so small that they're almost beyond comprehension, but they're also remarkably resilient. Some photons can travel billions of years, crossing vast stretches of space before reaching Earth. When we observe them, it's almost as if we're peering back in time, looking at the past encoded in their very being. This raises an intriguing question. Can photons remember where they've been? Can they carry any trace of their journey, almost like a cosmic memory? Photons, unlike anything we know on a human scale, don't age or slow down as they travel. Once they're set in motion, they continue moving in a straight line until something blocks them or changes their path. In the vacuum of space, there's little to stop them, so they travel uninterrupted. These tiny packets of light bring us images of distant galaxies, colorful nebulae, and the afterglow of the Big Bang itself. When we receive photons from the early universe, we're glimpsing the oldest light in existence. Unlike matter, which can absorb and retain physical marks from experiences, photons don't store information in a way that we can easily understand. But in quantum physics, the story is more complex. Photons don't exactly forget where they've been. Rather, they carry certain characteristics that seem to reflect their journey. For example, photons have a property called polarization, which describes the orientation of their wave-like motion. This polarization can change based on the environments they pass through, such as magnetic fields or dust clouds. In a sense, polarization acts as a marker of their path, encoding subtle hints of the places they've traveled. Another aspect of photons that's closely tied to their journey is their wavelength, which determines their color. A photon's wavelength can shift over long distances, especially in the vast expanding universe. This phenomenon, known as redshift, stretches the wavelength of light, shifting it toward the red end of the spectrum. Redshift is a direct record of the photon's long journey, providing us with clues about how fast its source is moving away from us. This stretching of light encodes information about the expansion of space, as well as the distance the photon has traveled. When they pass through interstellar clouds or come close to a black hole, they can be affected by the gravitational forces in those regions. A photon that has been gravitationally lensed carries with it a distorted image, altered by the gravitational field it encountered. This effect allows us to map out the distribution of mass across the universe, even when that mass isn't directly visible. In the quantum realm, particles like photons exist in a state of superposition, where they can take on multiple properties or paths simultaneously. The famous double-slit experiment shows how photons can behave as both particles and waves, depending on how they're observed. This experiment also suggests that photons don't take a single, straightforward path from one point to another. Instead, they travel as a probability wave, exploring all possible paths simultaneously. When a photon finally arrives, its specific path seems to collapse into a definite position. Some scientists wonder if this process could mean that photons retain a subtle probabilistic memory of all the paths they might have taken. In this way, a photon arriving from a distant star might carry with it traces of countless potential paths, shaped by every object and field it might have encountered. Photons can also be quantum entangled, which is a form of connection between particles that remain linked regardless of distance. When two photons are entangled, a change in one will instantly affect the other, even if they're light years apart. This entanglement seems to defy our ordinary sense of cause and effect, suggesting that photons might be linked in ways we don't yet understand. Entangled photons could, in theory, share information across great distances, even through the structure of space itself. In modern physics, there's also a theory called the holographic principle, which suggests that the universe might store information in a two-dimensional boundary. In this view, all of the information about a photon's journey, including its encounters and influences, could be encoded in the fabric of space-time itself. If the holographic principle holds true, then photons might be more than just messengers of light. They could be records woven into the very structure of the cosmos. Their journey might be written onto the boundary of the universe, allowing the past to influence the present in ways we're only beginning to understand. Some physicists go even further, proposing that the very nature of space and time might be linked to the paths of particles like photons. In certain theories, the motion of photons and other particles helps create the geometry of space itself. If this is true, then the journey of each photon isn't just a passive trip through space. It actively shapes the structure of the universe. In this view, photons don't just remember their paths. They help to create them, leaving behind a lasting trace of their passage in the form of space itself. Invisible galaxies. Could entire star systems be hiding in plain sight? In the vast reaches of the universe, it's possible that entire galaxies, full of stars, planets, and perhaps even life, are hidden from our sight. These are what scientists refer to as invisible galaxies. Unlike the bright galaxies we see in the night sky, these hidden galaxies are obscured, cloaked by dense clouds of cosmic dust, or composed mainly of a strange substance known as dark matter. Galaxies hidden by dust are the easier of the two types to imagine, although still difficult to detect. They're often located in star-forming regions, places where thick clouds of gas and dust swirl and condense, creating perfect conditions for new stars to form. When stars ignite within these dense clouds, they're often blanketed by the surrounding dust, which absorbs visible light, making the galaxy appear almost pitch black from our viewpoint. The dust acts like a cosmic veil, keeping the galaxy's light from reaching us in the usual wavelengths. But just because we can't see them in visible light doesn't mean they're completely undetectable. Using telescopes that detect infrared radiation, astronomers can sometimes peer through these thick dust clouds. Infrared light, with its longer wavelengths, can pass through dust more easily than visible light, revealing faint outlines of these hidden galaxies. Many of these dust-covered galaxies are located far from Earth, billions of light-years away. Because of their distance, the light we receive from them is not only dimmed by dust, but also stretched by the expansion of the universe, shifting it toward the infrared part of the spectrum. This shift is known as redshift. When scientists point infrared telescopes at the sky, they sometimes detect these faint red-shifted signals from galaxies hidden within dense clouds. These signals give us clues that invisible galaxies are out there, even if they're only faint shadows against the backdrop of space. But some galaxies remain hidden for a different reason altogether. They're not obscured by dust. Instead, they're made up mostly of dark matter, a substance that doesn't emit or reflect light in any detectable way. Dark matter doesn't interact with light or other electromagnetic radiation, which means it's entirely invisible to our telescopes. We only know it exists because of its gravitational effects on visible matter. When astronomers observe stars or galaxies behaving in strange ways, spinning faster than expected or bending light around them, they suspect dark matter is nearby, influencing these movements with its gravity. Dark matter galaxies, also called dark galaxies, are galaxies where dark matter vastly outnumbers regular matter. They have little or no visible stars, so they're almost impossible to detect without studying their gravitational influence. When astronomers observe the way light from distant galaxies bends around seemingly empty patches of space, they suspect there may be a dark galaxy lurking there, bending light with its gravitational pull. These dark galaxies could contain stars or other objects that are simply too faint to see, or they might be entirely composed of dark matter, with no visible stars at all. If dark galaxies exist in large numbers, they could represent a significant portion of the universe's mass. According to estimates, dark matter makes up about 85% of all the matter in the universe, with visible matter accounting for just a small fraction. If dark galaxies are common, they could explain where much of this dark matter resides, spread out in massive structures that we can't see directly. Finding them could help solve one of the biggest questions in modern physics. What exactly is dark matter, and how does it shape the universe? Dark galaxies could reveal new information about how galaxies form and evolve. In a typical galaxy, visible matter and dark matter interact, with dark matter acting as a kind of scaffolding that holds everything together. Dark matter's gravitational pull attracts gas and dust, providing a framework for stars and planets to form. But in a dark galaxy, this process might happen differently. With so little visible matter to work with, dark galaxies may evolve on a completely separate path. Studying these dark galaxies could give us a glimpse of what the universe looked like before the first stars formed, when dark matter dominated and visible matter was rare. Detecting these hidden galaxies is an enormous challenge, but scientists are developing new methods to search for them. Some researchers use a technique called weak gravitational lensing, which involves studying tiny distortions in the light from distant galaxies. When light from a distant galaxy passes near a dark matter galaxy, it bends slightly, creating a tiny faint arc in the sky. By carefully analyzing these arcs, astronomers can map out where dark matter galaxies might be. Weak gravitational lensing has already revealed several potential dark galaxies, though confirming them is a complex process that requires more detailed observations. Another technique involves looking at how galaxies are clustered across the sky. Visible galaxies tend to cluster in certain patterns, pulled together by gravity. If dark galaxies exist, they would likely follow similar clustering patterns influenced by the same gravitational forces. By mapping the distribution of visible galaxies, scientists can make predictions about where dark galaxies might be hiding. This method relies on statistical models, so it doesn't give a direct view of the dark galaxies, but it helps researchers narrow down where to look. Echoes of the Big Bang, fossil sounds from the dawn of time. In the depths of space, a faint ancient signal is traveling endlessly through the cosmos. This signal, known as the cosmic microwave background, or CMB, is often called the echo of the Big Bang. It's a kind of radiation that was released not long after the universe began, and it still carries a trace of the heat and energy from those earliest moments. For scientists, the CMB is like a fossil of sound, a relic that holds information about the universe's beginnings. In the earliest moments after the Big Bang, the universe was a chaotic place. It was incredibly hot and dense, with particles of energy and matter packed tightly together. In this intense environment, particles constantly collided and interacted, creating waves of sound that rippled through the primordial plasma, a thick, dense soup of particles that made up the early universe. These sound waves, or pressure waves, were created by the tiny fluctuations in density within this plasma. Higher density areas would compress, creating peaks, while lower density areas would expand, forming valleys. This movement generated waves of pressure or sound that traveled across the young universe. But this sound wasn't something you could hear with your ears. The early universe's sound waves were vibrations in the plasma, not sounds in the way we know them on Earth. These were waves of pressure and temperature changes moving through a dense medium, much like the way sound waves travel through the air here on Earth. Over time, as the universe expanded and cooled, these waves stretched out, becoming larger and slower. Eventually, around 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine and form neutral atoms. At this point, the universe became transparent to radiation, meaning that light and other forms of electromagnetic radiation could finally travel freely through space. This is the moment when the CMB was born. With particles no longer colliding constantly, the sound waves faded, leaving behind a faint radiation signature that still exists today. This radiation is what we detect as the CMB, and it carries a faint imprint of those early sound waves. By studying the CMB, scientists can observe the patterns of these ancient waves and learn about the conditions in the early universe. When astronomers first discovered the CMB in 1964, they weren't sure what it was. Two scientists, Arno Penzias and Robert Wilson, were conducting experiments with a radio antenna and kept picking up a faint, persistent noise coming from all directions in space. They checked for local sources of interference, even cleaning out pigeons nesting in the antenna, but the noise persisted. Eventually, they realized that they had stumbled upon something extraordinary, a faint hum left over from the dawn of the universe. Today, scientists study the CMB with highly sensitive instruments, including satellites like the Planck Space Observatory. These instruments allow them to map out the CMB in extraordinary detail, detecting tiny variations in temperature and density across the sky. The CMB isn't uniform. It contains small, hot and cold spots, which are areas of slightly higher or lower energy. These variations correspond to the density fluctuations in the early universe, the same fluctuations that created the sound waves back then. By mapping these variations, scientists can create a picture of what the universe looked like in its infancy. They can see how matter was distributed, which areas were denser or less dense, and where those early sound waves left their marks. These maps are incredibly detailed, showing subtle differences in temperature that are only a fraction of a degree. Yet, even these tiny differences hold valuable information about the forces that shaped the universe in its first moments. One fascinating discovery from the study of the CMB is that the early universe was ringing with sound waves in a way that influenced the distribution of galaxies we see today. These ancient sound waves, called baryon acoustic oscillations, left faint ripples that still influence the large-scale structure of the cosmos. Galaxies tend to cluster in patterns that reflect the original sound waves from the Big Bang, forming subtle rings and clusters on a cosmic scale. By studying the CMB, scientists can trace these patterns back to their origins, connecting the galaxies we see today to the sound waves that rippled through the universe billions of years ago. The CMB also hints at what the very first moments after the Big Bang were like. Scientists have used it to investigate a period called inflation, a phase of rapid expansion that is thought to have occurred just fractions of a second after the universe began. During inflation, the universe expanded faster than the speed of light, stretching out tiny quantum fluctuations into larger patterns that would later become the seeds of galaxies. The traces of inflation are imprinted in the CMB in the form of tiny irregularities. Listening to the CMB is a bit like listening to a fossilized recording of the universe's birth. Even though we can't hear it as sound, the CMB holds echoes of the first vibrations that rippled through space. This ancient signal connects us to a time when the cosmos was just beginning, giving us a glimpse of how it all started. It's a reminder that, even in the vast silence of space, there are traces of activity and movement, recorded in ways we're only beginning to uncover. Despite all the information it provides, there are still mysteries hidden within its patterns. Some parts of the CMB are puzzlingly different from what we would expect. For example, there's an area called the cold spot, which is significantly cooler than the surrounding regions and doesn't fit neatly into the current understanding of cosmic history. Some speculate that this cold spot could be evidence of unusual cosmic events, possibly even something as crazy as a collision with another universe. Galactic ghosts. Are there galaxies that faded before we found them? Galaxies are some of the most massive structures in the universe, filled with stars, gas, and dark matter, all held together by gravity. They're like cosmic cities, with countless stars shining brightly for billions of years. But what if some galaxies have come and gone before we ever got the chance to observe them? Galaxies don't just disappear overnight. The process of fading, if it happens, would be a gradual one, spanning millions or even billions of years. The light we see from distant galaxies takes an incredible amount of time to reach us. When we observe galaxies billions of light years away, we're seeing them as they were billions of years ago during the early stages of the universe. Some galaxies we observe today might have already vanished, their stars burned out, their gas depleted, leaving behind a dark, quiet skeleton of what once was. One way a galaxy might fade is through a process called quenching. Galaxies need gas to form new stars, and without a steady supply of gas, they eventually run out of fuel. This can happen when galaxies use up most of their gas, or when powerful forces like supermassive black holes or interactions with other galaxies strip the gas away. When star formation stops, the existing stars in a galaxy continue to shine, but without new stars to replace them, the galaxy slowly dims over time. The older stars eventually reach the ends of their lifetimes, becoming white dwarfs or black holes, and the galaxy becomes less and less visible. Some galaxies may also lose their brightness due to interactions with other galaxies. When galaxies collide or come close to each other, their gravitational forces can disrupt their shapes, strip away their stars, and send streams of gas and stars into space. These interactions can sometimes trigger bursts of new star formation, but in other cases, they can tear galaxies apart, leaving only faint traces behind. Over time, a galaxy that was once bright and active might become little more than a ghost, a scattered collection of dim stars and gas with no clear structure. In some cases, a galaxy might be swallowed up by a larger galaxy. When this happens, the stars, gas, and dark matter of the smaller galaxy are absorbed into the larger one. The remnants of the smaller galaxy blend into the structure of the larger galaxy, becoming part of its outer halo or spiral arms. This process is known as galactic cannibalism, and it's thought to be common in galaxy clusters, where galaxies are packed closely together. After merging, the smaller galaxy essentially disappears as a distinct entity, leaving behind only faint traces in the form of faint star clusters or orbiting the larger galaxy. There's the possibility that some galaxies faded due to interactions with dark energy. In regions where dark energy is especially strong, it might disrupt galaxies, pulling them apart and thinning out their structure. Galaxies in these regions might become stretched and distorted, eventually spreading out so much that they no longer appear as distinct entities. Instead, they might dissolve into a diffuse cloud of stars and gas, becoming a barely detectable presence in the universe. There are also cosmic structures known as tidal streams, which are long, thin trails of stars left behind by galaxies that have interacted or merged. These streams are like fingerprints, traces of galaxies that might have faded or disappeared after merging with larger galaxies. When astronomers map out these tidal streams, they can piece together the history of galactic interactions, finding evidence of past galaxies that no longer exist as separate entities. Galaxies in a deep freeze, the coldest reaches of known space. In the vast reaches of the cosmos, there are areas so cold that they approach what scientists call absolute zero, the lowest possible temperature in the universe, where even atoms nearly stop moving. In these regions, temperatures sink to unimaginable lows, sometimes only a fraction of a degree above absolute zero, which sits at minus 273.15 degrees Celsius or minus 459.67 degrees Fahrenheit. In these regions, matter behaves in ways that seem almost alien, providing a glimpse into an environment that defies the typical warmth of stars and the activity of galaxies. Deep space, far from any heat-producing stars, is where these icy pockets of near absolute zero are most often found. Here, energy is sparse, leaving atoms and molecules in a sort of suspended state, barely vibrating. In these frigid zones, familiar materials such as hydrogen gas can become incredibly dense or form exotic structures. When temperatures dip this low, gas particles, which would usually zip around at high speeds, slow down dramatically. Some can even form what scientists call a Bose-Einstein condensate, where particles lose their individual identities and behave as one giant superparticle. These condensates exhibit strange properties, like flowing without resistance, or even defying gravity in certain lab conditions. Scientists wonder if some of the coldest places in the universe might naturally host this kind of exotic matter, though they have yet to observe it outside of Earth-based experiments. These deeply cold parts of space are sometimes found around dead stars like white dwarfs or neutron stars, where the absence of fuel and radiation leads to an almost eerie stillness. A neutron star is the leftover core of a massive star that exploded in a supernova, leaving behind a compact, incredibly dense object. Around it, temperatures can drop sharply because all the energy from the original star has dissipated and no new heat is being generated. Over billions of years, the space around such stars cools even further, leaving regions of extreme cold where only faint traces of energy remain. If we were able to visit these areas, it might be like entering a void with no warmth, no motion, and a stillness that stretches across light years. One of the coldest natural environments ever observed in the universe is the Boomerang Nebula, a cloud of gas located about 5,000 light-years away in the constellation Centaurus. The Boomerang Nebula is so cold that its temperature is just about 1 degree above absolute zero. What makes this nebula unique is that it's actually cooling itself as it expands. As the gas spreads out, it loses heat in a process similar to how air cools when it expands from a spray can. This chilling effect has led scientists to describe the Boomerang Nebula as the coldest place in space that we know of. Cold, however, doesn't mean completely inactive. Even in these frozen regions, there's still the presence of matter, energy, and subtle forces at work. Atoms and particles behave differently in these conditions, and scientists believe that strange, barely understood states of matter could exist there. For example, in the harsh cold, hydrogen atoms can form into a kind of molecular snow, accumulating on dust grains and creating tiny, icy particles that might drift slowly in space. This cosmic snow isn't the kind of soft snow we see on Earth. It's solid and dense, forming a layer over grains of space dust that may eventually contribute to forming new stars and planets. The regions near absolute zero are also places where quantum effects, usually hidden in warmer environments, can come to life on a grander scale. In these ultra-cold areas, particles like electrons and protons can act in ways that defy the usual laws of physics. They can overlap, become entangled with one another, or even pass through barriers in a way that would be impossible at higher temperatures. This means that even in the frigid emptiness, particles might be engaging in a delicate quantum dance, where they subtly influence each other across vast distances. In some cold parts of space, simple molecules that are crucial to life can form and survive for extended periods. Without heat, chemical reactions slow to an incredibly sluggish pace, but this doesn't mean they stop entirely. Over millions of years, atoms of carbon, hydrogen, oxygen, and nitrogen, the building blocks of organic molecules, can slowly bond together in these cold, sheltered environments. Some scientists suggest that these cold clouds of molecules could act as a cosmic nursery for complex chemistry, where the first steps toward life may begin in a frozen state. These molecules might travel for millions of years across space before they end up in warmer environments, where their stored potential could finally spark life. Scientists studying these ultra-cold regions are continually surprised by the ways in which matter seems to adapt to the lack of heat. Dust and gas clouds, for example, may form intricate structures under the influence of even the faintest gravitational pulls. Clumps of matter can slowly come together to form icy crystals, which might look like ghostly shadows in the vast darkness. The lack of energy also means that magnetic fields, which usually shape and guide particles, have a much weaker influence. Without strong magnetic fields, particles drift more freely, leading to patterns that are gentle and diffuse. These cold regions serve as laboratories for scientists seeking to understand not only matter, but also the fundamental forces at play in the universe. In recent years, researchers have been developing ways to simulate these conditions on Earth, hoping to create environments that reach close to absolute zero in laboratory settings. By observing how atoms and particles behave in these ultra-cold conditions, they aim to gather clues about the larger-scale structures we observe in space. Beyond darkness, what lies outside the edge of our universe? As far as our most powerful telescopes can reach, the universe seems to stretch endlessly, filled with stars, galaxies, clusters, and nebulae. Does the universe have an edge, or does it extend forever, with stars and galaxies filling it infinitely? And if there is an edge, what lies beyond it? One idea about the boundary of our universe comes from what's known as the observable universe. This isn't necessarily an edge in the traditional sense. Rather, it's the limit of what we can see based on the distance light has traveled since the beginning of the universe. Since the universe is about 13.8 billion years old, we can only observe objects whose light has had time to reach us within that time frame. This gives us a bubble of visibility, roughly 93 billion light-years across, beyond which things might still exist but remain forever unseen, simply because their light hasn't yet reached us. But outside this observable sphere, what lies beyond? If the universe is finite, does it come to a hard stop, or does it curve back on itself like the surface of a sphere? Many scientists propose that the universe could be curved in a way that if you traveled far enough, you would eventually end up back where you started, just as if you were traveling on the surface of a planet. This idea suggests that, rather than having an edge, the universe is self-contained and wraps around, making it impossible to ever reach an outside. If this theory holds, space could be like a looping map, extending forever without a true end. Some theories suggest, however, that the universe could indeed have an outside in a way that's difficult to picture. In the multiverse concept, our universe might be just one of countless other universes, each existing within a larger, possibly infinite structure. Some have also considered the possibility of other dimensions existing beyond our three-dimensional understanding of space. In theories that attempt to unify all forces of nature, like string theory, additional dimensions beyond the ones we experience daily may exist. While we're used to thinking of space in terms of length, width, and height, these theories suggest there could be extra dimensions curled up in such tiny scales that they're hidden from our perception. If we could somehow access or perceive these dimensions, they might reveal entirely new kinds of spatial relationships or places that are currently unimaginable. Just as a bubble has an inner and outer surface, some theories suggest that our universe might have a shape that implies an outside environment with its own strange properties. In these models, the shape of the universe determines how it behaves at its outer edges, where space might bend or twist in ways that aren't visible within our usual experience. At this boundary, if it exists, matter might behave differently, or the forces we know, gravity, electromagnetism, might weaken or change altogether. There's also the notion that our universe might be constantly expanding into something, but it's not expanding into another place, as we would understand it. Instead, it's thought to be stretching space itself. The expansion of the universe, observed in the redshifts of distant galaxies, suggests that space is continuously growing, making room for galaxies to drift farther apart. However, if space itself is growing, is it pulling more matter or energy from somewhere outside? Or does this expansion have a limit? Some theories suggest that our universe could be like a bubble forming within a much larger cosmic sea. This sea might have no recognizable matter, light, or energy in the way we know it. Perhaps it's a domain filled with what scientists call quantum foam, a frothing field of energy at unimaginably small scales. In this view, our universe could be one bubble in a vast ocean of such bubbles, each with its own properties, expanding and possibly even colliding with others in rare cosmic events that would affect both universes involved. It's also possible that what lies outside of our universe is something beyond space and time as we understand them. In the earliest moments of the Big Bang, conditions were so extreme that space and time had not yet solidified into the forms we experience today. If we could somehow peer beyond the universe, we might find a realm where our familiar rules of reality break down entirely. This outside could be a zone of pure potential, a kind of canvas upon which the universe continually emerges. Magnetic hurricanes, swirling, invisible storms in intergalactic space. In the deep, empty spaces between galaxies, forces move and shape the universe in strange ways. Among these forces are intense magnetic fields that, in some regions, spin and twist like invisible hurricanes. Though unseen, these swirling magnetic storms can have surprising effects on anything that passes through them, like particles, light, and even entire star systems. These magnetic hurricanes are often found in regions where magnetic fields are especially intense. Unlike the steady, uniform magnetic fields we see in simpler environments, these fields are full of energy and turbulence, twisting like cyclones and spiraling as they grow. They create powerful currents that act almost like whirlpools in the vast cosmic sea. Particles that encounter these fields don't simply move in straight lines. Instead, they're tossed, redirected, and sometimes accelerated to astonishing speeds by the spinning magnetic forces. When high-energy particles, like cosmic rays, meet these magnetic hurricanes, the results can be startling. Cosmic rays are some of the fastest particles in the universe, traveling vast distances across galaxies, often nearly at the speed of light. But when they encounter a magnetic storm, their paths bend and curve, caught in the magnetic winds. These particles may spend thousands, even millions of years, spinning through these regions, trapped in loops until they finally escape. Though light isn't affected by magnetic fields directly, when it passes through magnetic regions filled with charged particles, strange things can happen. In a process called Faraday rotation, the polarization of light changes, twisting slightly as it moves through the magnetic field. Over long distances, this effect can actually help scientists measure the strength of these invisible storms, giving us a way to observe their impact on the cosmos. Each tiny twist or shift in light that passes through tells us more about the strength, structure, and nature of the magnetic hurricane that altered it. In some areas, astronomers see entire galactic clusters, huge groupings of galaxies, moving in ways that suggest they're feeling the pull of unseen magnetic fields. It's possible that magnetic hurricanes, with their intense energy, create currents or flows that gradually shape and direct the movement of galaxies over millions of years. Much like ocean currents shape the movement of water across Earth's seas, these magnetic currents might influence the movement of matter on a scale so vast it's nearly impossible to measure in human terms. One of the biggest mysteries is what causes these magnetic storms to form in the first place. Some scientists think that galaxies themselves are involved, with rotating stars, gas clouds, and magnetic fields combining to create turbulent magnetic environments that eventually spill out into intergalactic space. Other researchers believe that these fields might be leftovers from the early universe, relics of the chaotic, high-energy conditions that existed shortly after the Big Bang. Whatever their origin, it's clear that these magnetic hurricanes are more than just a cosmic oddity. They are powerful forces that shape space in unexpected ways. The intensity of these magnetic fields also creates extreme conditions where scientists think unusual forms of matter might emerge. Just as extreme temperatures and pressures on Earth can change the properties of materials, the intense magnetic forces in these storms might do the same in space. The long-distance pulse. Do distant galaxies beat like hearts? Some astronomers speculate that galaxies might be sending out periodic pulses, much like heartbeats. These pulses, if they exist, are not like any familiar signals. They wouldn't be flashes of light or bursts of radio waves, nor anything we could hear. Rather, these pulses would be subtle, periodic shifts in gravitational forces, almost like gentle cosmic rhythms that only the most sensitive equipment might one day detect. Galaxies are not isolated. They belong to clusters and superclusters that move together through space. Within these structures, gravitational forces are constantly at work, tugging and twisting galaxies as they orbit each other. It's possible that these gravitational interactions create regular, slow changes in galaxies' positions or structures. Imagine a galaxy in a dense cluster surrounded by others. The gravitational tides from nearby galaxies might cause it to stretch or compress, then release, over the course of millions or even billions of years. If we could observe this over long periods, we might notice patterns, subtle and slow, but rhythmic, like a cosmic pulse. Another possible source of these pulses could be the presence of supermassive black holes at the centers of many galaxies. These black holes are known to consume matter in bursts, sometimes swallowing gas and stars from their surroundings, and then emitting powerful energy as a result. If these feeding cycles happen in intervals, they might cause a ripple effect throughout the galaxy. Picture a galaxy's black hole suddenly drawing in a large cloud of gas. This massive influx of material could trigger waves of energy that pulse outward, shaking the galaxy's structure in a way that could eventually propagate through space, like faint, distant beats. Clusters of galaxies are also not static. They drift through space and sometimes crash into each other in slow-motion cosmic collisions. These interactions take billions of years, but as clusters interact, their combined gravitational fields could create waves that pulse outward. In these moments, enormous amounts of energy would be released, possibly creating periodic beats that ripple through space, like shock waves from a distant explosion that continues for eons. The pulses would be extremely faint and difficult to detect from Earth, but they might still leave a mark on the structure of space itself. Some researchers wonder if these cosmic pulses, if they exist, might be detectable in the CMB. The CMB is sensitive to changes in the structure of space, and it might carry faint traces of pulses from massive ancient events. If galaxy clusters or supermassive black holes are producing these rhythms, they might leave subtle imprints in the CMB. The distances between galaxies are enormous, and any signal would weaken as it travels across millions or billions of light years. Earth's telescopes are not yet sensitive enough to measure the small periodic changes in gravitational fields that would indicate a galactic pulse. But with advances in gravitational wave detectors, scientists are slowly becoming able to sense smaller and smaller fluctuations in the fabric of space. One day, these detectors might be sensitive enough to pick up faint rhythms from distant galaxies. If we observe certain galaxies or clusters over long periods, we might begin to see regular, subtle shifts in their positions or shapes. This would be a painstaking process, requiring vast amounts of data and precise measurements, but it's possible that scientists could eventually detect patterns that reveal a rhythm. By tracking these changes, astronomers might begin to decode the heartbeat of galaxies, if it exists, and understand what forces create it. Quantum time locks. Are there paused regions in the cosmos? Imagine a part of space where time itself slows to a crawl or even comes to a stop, creating a pause in the universe's story. This concept, strange as it seems, finds some grounding in theories within quantum mechanics. Quantum mechanics suggests that time and space might not always act in predictable ways. Tiny particles, like electrons or photons, have behaviors that defy common sense. They can be in two places at once, jump instantly from one state to another, and sometimes pause in one state before resuming their path. Now, scientists wonder if something similar could happen on larger scales, creating regions in space where time seems frozen. One possible cause of these paused regions could involve extreme conditions where the laws of physics break down, such as in the intense gravity of black holes. Near the edge of a black hole, time behaves differently. For an observer far from the black hole, anything falling toward it seems to slow down as it nears the event horizon. In theory, this phenomenon of freezing could extend beyond black holes, possibly happening in regions where spacetime is severely warped by gravity or other forces we don't yet fully understand. Quantum theories open up the possibility of time locks or frozen moments in regions far from black holes. Quantum fluctuations, tiny bursts of energy that appear and vanish on the smallest scales, could create brief pauses or anomalies. In empty regions of space, far from stars or galaxies, these quantum events might even linger, building up over time and creating a zone where time behaves strangely. Just as quantum particles can experience superpositions, existing in multiple states simultaneously, perhaps regions of space can exist in a superposition of time states, where time both moves forward and, in some sense, stays still. Theories of cosmic inflation, which describe the rapid expansion of the universe just after the Big Bang, hint at frozen regions. During this period, space expanded so quickly that some areas effectively froze in place relative to others. This means that in the earliest moments of the universe, certain regions may have become locked in a slower timeline compared to surrounding space. If inflationary zones still exist in some far-off, untouched regions of the universe, they could act like frozen pockets where time has not yet caught up to the rest of the cosmos. These time-locked regions would be incredibly difficult to detect. They wouldn't emit light or energy in the usual sense, and they might appear as dark, empty voids from our perspective. But scientists speculate that these regions could affect the path of particles or light that pass nearby. For instance, a photon traveling near a paused region might experience a slight delay, almost as if it were encountering an invisible obstacle. This delay could, in theory, be detectable over long distances. If time is nearly stopped in certain areas, any particles or objects within them would also be paused. Imagine a small dust cloud or gas particles trapped in a region where time barely moves. They would seem frozen, as if held in place, perhaps for millions or billions of years. To anything outside, they would appear suspended, waiting for time to resume its flow. If time were to start moving normally again in these regions, the particles would pick up right where they left off, continuing their journey as if no time had passed at all. Since quantum mechanics allows for spontaneous changes in states, a paused region might unlock itself at random, with time suddenly resuming for the matter inside. To an observer outside, this would look like a sudden release. Such events could cause tiny, unexplained shifts in the paths of particles or light that pass by, a sign that some kind of temporal anomaly has reset in space. We tend to think of time as constant, flowing at the same rate everywhere, but if paused regions exist, time may not be as uniform as we imagine. They raise questions about whether the universe has multiple layers of time, each interacting differently depending on the conditions within each layer. It's a mind-bending thought that different parts of the universe might exist in different timelines, each advancing at its own pace. Galactic eyes, strange structures that appear to be watching us. Though it's probably just a cosmic coincidence, some galaxy formations bear an eerie resemblance to eyes, large and wide, set against the backdrop of the universe. One well-known example of an eye in space is the Ring Galaxy, or the Cartwheel Galaxy, located about 500 million light-years away in the constellation Sculptor. The Cartwheel Galaxy is a striking structure, with a bright core surrounded by a nearly circular ring of stars and dust, resembling a pupil and iris. This shape was likely created by an enormous collision with another galaxy, sending shockwaves through the cartwheel's core and creating a rippling ring of newly formed stars that spread outward. While we see it as an eye, it's actually a chaotic aftermath of galactic interactions on an unimaginably large scale. Yet the pattern it forms speaks to a curious kind of symmetry. Other galaxies also seem to form eye shapes through similar gravitational encounters. When galaxies collide, their massive gravities pull and stretch each other, often producing intricate patterns, loops, and arcs of stars and gas that can resemble human-like features. In some cases, the central cores of interacting galaxies line up with spiral arms or outer rings to create shapes that look remarkably like an eye peering into space. These formations are temporary, of course. Over millions or even billions of years, the forces of gravity will continue to pull, merge, and reshape these galaxies, erasing the eye-like appearance and leaving behind new hybrid galaxies. This tendency of ours to recognize faces, eyes, and shapes in things as simple as clouds or as vast as stars is known as pareidolia. Seeing eyes in galaxies might simply be our brain's way of finding something recognizable in the immense, unfamiliar patterns of space. Yet, it's fascinating to consider how patterns from our everyday world echo back at us from hundreds of millions of light years away in structures that bear no real relationship to human forms. Some entire galaxy clusters can also form patterns that resemble eyes. These clusters, often shaped by the gravitational pull of dark matter, sometimes gather in a way that forms elliptical shapes with bright central regions. If two clusters happen to line up, one slightly offset from the other, it can create the illusion of an enormous eye with a central pupil, where the galaxies are densest. These massive galactic eyes are reminders of the scale of the universe. Another way that eyes emerge in space is through gravitational lensing. This bending can create arcs, rings, or multiple images of the same object, all of which depend on the angle of observation. When the lensing effect is especially strong, it can produce a full ring of light, known as an Einstein ring, surrounding the massive object in front. This creates an eye effect, with the lensing galaxy as the central pupil and the ring as the iris. For instance, the galaxy cluster Abell 68 creates a powerful lensing effect that, from certain angles, produces ringed structures with eerie resemblance to eyes gazing back at us. This optical trick, produced by warped spacetime itself, is one of nature's most dramatic illusions. Dark stars, theories on stars made of exotic matter. Imagine stars that exist without light, hidden from our view and shrouded in shadows. These stars wouldn't shine in any way we recognize. Instead, they might consist of mysterious, exotic particles or dark matter, making them dark stars. They would not radiate or emit the familiar light or heat that we expect from stars like our Sun, but their mass would still impact the space around them, tugging at nearby objects and subtly influencing their movements. One of the core ideas behind dark stars is that, unlike regular stars composed mostly of hydrogen and helium, these stars could be made up of exotic particles we've only theorized about. Among the leading candidates for such particles is dark matter. We know dark matter exists because we can observe its gravitational influence on galaxies, but we can't see it directly. It doesn't emit or reflect light, and it doesn't interact with electromagnetic forces in the way regular matter does. If enough dark matter particles clump together under gravity, they might form structures large and dense enough to qualify as stars, even if they remain dark to our eyes. If dark matter can clump into stars, it would be one of the strangest forms of matter in existence. These dark stars wouldn't shine because they wouldn't undergo nuclear fusion. Without fusion, dark stars would be colder and essentially invisible. Their gravitational pull, however, would still be immense, marking them as massive ghostly objects lurking within the universe. In theory, they could float undetected between galaxies, or even lie within our own Milky Way, where their presence would go unnoticed unless they affected the motion of nearby stars. Some scientists think dark stars could form from theoretical particles known as WIMPs, weakly interacting massive particles, which are thought to make up dark matter. WIMPs would have mass and feel the pull of gravity, but they would barely interact with other particles, passing through regular matter without making much contact. If WIMPs could clump together under gravity, a large enough collection might form a stable structure, essentially creating a WIMP-based star. Since dark stars emit no light, telescopes cannot detect them directly. Instead, astronomers must rely on indirect methods to infer their presence. For instance, the gravitational pull of a dark star on nearby visible stars could create a detectable wobble or tug, indicating something massive but invisible nearby. In dense star clusters, such as those in the centers of galaxies, scientists could look for slight shifts in star positions that hint at dark objects exerting force from within the cluster. Gravitational lensing could also be useful. Dark stars could potentially have formed during the earliest days of the universe. In the period following the Big Bang, known as the Dark Ages of the cosmos, ordinary stars had not yet ignited. In this dark primordial era, dark matter might have begun clumping into massive objects, forming dark stars. These early stars, if they existed, would be remnants of the universe's first structures, surviving in the background long after ordinary stars began to dominate the cosmos. If we could detect such ancient dark stars, we'd be looking back at some of the first cosmic structures ever formed, shedding light, ironically, on a time when there was no light at all. Some scientists speculate that dark stars might have evolved alongside regular stars, quietly populating the universe. As regular stars exhaust their fuel and collapse into black holes, dark stars could persist far longer, unaffected by the aging processes that affect ordinary stars. In this way, dark stars could be incredibly long-lived, their lifespans far outlasting the hottest and brightest stars in the cosmos. They might be considered cosmic fossils, spanning eras of cosmic history we can only imagine. Finding a dark star would be one of the most significant discoveries in modern astrophysics, revealing a form of matter or energy entirely unlike anything we have observed before. It would open up new questions. What other structures could dark matter form? Could there be dark galaxies, star systems, or even planets composed of exotic particles? Cosmic bruises, mysterious cold spots that defy explanation. Across the vast canvas of the cosmos, scientists have discovered patches known as cold spots that appear in the CMB. The largest and most famous of these cold patches, often called the cold spot, is a region that stands out in the otherwise uniform microwave radiation, creating a curious and unexpected bruise in the universe. The cold spot, which spans around 1.8 billion light-years, appears as a region about 0.00007 Kelvin, or 70 microkelvin colder than the average CMB. Typical temperature variations in the CMB range around 18 microkelvin. Scientists first detected it in data from NASA's WMAP, the Wilkinson Microwave Anisotropy Probe, satellite in the early 2000s, and it was later confirmed by the European Space Agency's Planck satellite. While tiny temperature fluctuations in the cosmic microwave background are expected and help scientists understand the distribution of matter in the early universe, a patch of this size and coldness stands out as unusual. The universe, as far as we know, shouldn't have cold spots this pronounced. This strange feature has inspired numerous theories as researchers try to uncover what might be hiding within this cosmic bruise. One of the main theories proposes that the cold spot may result from a vast supervoid, an enormous region with fewer galaxies and clusters than typical space. In the same way that a dense galaxy cluster can warm up the background radiation slightly by gravitationally pulling on light, a void might cool it. Photons traveling through a supervoid would experience less gravitational pull along the way, losing some energy as they cross and leaving a cooler imprint. However, even if a supervoid exists in this region, it doesn't completely account for the temperature drop scientists see in the cold spot, suggesting there may be additional factors at play. Some have speculated that it could be evidence of something even more unusual, a point of contact with another universe. According to some models, universes could collide or interact with one another, especially in their early stages of formation. This collision wouldn't look like a traditional impact, but might instead leave subtle effects, such as imprints on the cosmic microwave background. A cold spot in the CMB could be the faint scar left over from a close brush or interaction with another universe that left its mark on ours before pulling away. If the cold spot truly is evidence of an interaction with another universe, it would suggest that the cosmos extends far beyond our observable limits. According to cosmic inflation theory, different regions of the early universe may have expanded at slightly different rates. These fluctuations in inflation could leave lasting imprints on the cosmic microwave background, creating regions of varying temperatures. If the cold spot is a relic of these early inflationary processes, it might provide insight into what was happening just moments after the Big Bang, potentially giving us clues about how the universe expanded and the forces that shaped it. Some theories even touch on the idea of cosmic defects or topological defects, which are thought to be leftover irregularities from the early universe. These defects could take various forms, such as strings or walls, that form when different regions of space with slightly different physical properties meet. If such a defect exists near the cold spot, it might explain the temperature anomaly by creating an area with unique physical characteristics, including cooler radiation. Gravitational whispers. Do black holes communicate? Black holes are often imagined as the ultimate loners. These cosmic enigmas seem to be entirely isolated, swallowing everything that dares to come too close. But over time, we've begun to learn that black holes may not be completely silent. Instead, they might send out faint, detectable signals that ripple through space. This doesn't mean black holes are speaking in any way we would recognize. But in the form of gravitational waves and subtle energy emissions, black holes might be able to share information across enormous distances. One of the most significant discoveries of the last decade has been that of gravitational waves, ripples in the fabric of space-time itself, first predicted by Einstein's theory of general relativity. These waves occur when massive objects accelerate or collide, like when black holes merge. When two black holes spiral toward each other, the immense energy of their collision sends out waves that spread across the universe, carrying information about the mass, distance, and motion of the colliding bodies. In a way, these gravitational waves act like messages. Although incredibly faint, they provide a record of the black hole's interactions, allowing us to catch glimpses of these invisible giants from billions of light-years away. When scientists first detected gravitational waves in 2015 with the LIGO Observatory, they confirmed that black holes could indeed announce their presence through these space-time ripples. But gravitational waves are only one type of signal that black holes might send. Some researchers believe that under the right conditions, black holes could emit other types of signals or phenomena that could travel through the cosmos. These signals might not be as dramatic as gravitational waves, which require a significant event like a merger. Instead, they could be more like quiet whispers, faint disturbances, or emissions that hint at the inner workings of these mysterious objects. There's also the question of whether black holes could release information through a phenomenon known as Hawking radiation. Named after the physicist Stephen Hawking, who first proposed the idea, Hawking radiation is a theoretical process in which black holes slowly lose mass and energy over time. According to Hawking's theory, this radiation is created by the strange quantum effects that occur near the black hole's event horizon. As pairs of particles pop in and out of existence in the vacuum of space, sometimes one particle falls into the black hole while the other escapes, carrying away a tiny bit of the black hole's energy. Over an unimaginable timescale, this gradual process could eventually cause the black hole to evaporate completely. If Hawking radiation exists, and it hasn't been directly observed yet, it raises interesting questions about the information black holes might release over time. Since black holes are believed to trap everything that falls into them, they seem to create a paradox. If information falls into a black hole, does it disappear forever, violating the principles of quantum mechanics? Or could Hawking radiation somehow encode some trace of that information as it escapes? Some scientists theorize that, in a way, black holes might whisper this information back into the universe bit by bit as they emit Hawking radiation, leaving behind clues about everything they've absorbed over their long lifetimes. Some researchers even propose that black holes might act as beacons of information through quantum entanglement. In theory, particles that fall into a black hole could remain entangled with particles outside it, creating a kind of link between the black hole and the outside universe. Though we don't yet understand how or if this connection could work in practice, it opens up the possibility that black holes might participate in some form of information exchange that bypasses the usual limits of space and time. All this brings up the question of whether black holes could eventually be used as a means of actual communication across vast distances. Some physicists speculate that advanced civilizations might one day be able to harness black holes as cosmic transmitters. By carefully manipulating matter around a black hole or using gravitational waves, these civilizations might be able to send signals or even encode messages within the structure of space-time itself. This idea is far beyond our current technological capabilities, but it raises the tantalizing possibility that black holes could serve as tools for interstellar communication in the distant future. The Great Galactic Leap. Are we slowly falling toward another universe? Imagine the universe as an enormous ocean, vast and mysterious, filled with waves and currents that move on scales too immense for us to comprehend fully. Some believe that galaxies, stars, and even the entire observable universe might be drifting within this ocean, not just in a slow movement across space, but perhaps towards a slow-motion approach to an entirely different universe. In our current understanding, galaxies are moving, each pulled along by the combined gravitational forces around them. This movement is often described as the cosmic flow. On the grandest scales, scientists have noticed certain patterns in this flow that can't be entirely explained by the galaxies and mass we see. It's as though there are gravitational forces tugging on galaxies from somewhere far beyond what we can observe. Some researchers refer to this mysterious force as dark flow, suggesting that vast amounts of matter or energy lie beyond the reach of our telescopes, guiding galaxies like a cosmic tide. One theory that's emerged is that this gravitational pull could be coming from another universe, or perhaps from a cluster of other universes. If this pull is indeed real, it's possible that small interactions between these universes are already taking place. Imagine two immense drifting ships passing each other in the night. While they may not touch, their gravitational fields still create effects in the water and the air around them. In the same way, some scientists think that as universes get closer, they might produce subtle changes in the structure of space, even leading to minor leaks between realms. These leaks wouldn't be dramatic. No sudden portals opening in space, but more like tiny weaknesses or points where the structure of one universe brushes against the other, perhaps allowing the exchange of exotic particles or unknown energies. If these leaks allowed even a small fraction of unknown particles to enter our universe, they might interact in strange ways with ordinary matter, possibly leaving traces we could detect. While the idea of two universes slowly approaching each other might seem improbable, there are parallels to be found in the cosmos. Galaxies themselves often collide and merge, drawn together by their gravitational fields. When this happens, the stars within those galaxies are flung into new orbits. Gas clouds collide and form new stars, and the galaxies themselves often settle into new shapes over millions of years. If two universes ever did get close enough to truly interact, the effects might be equally transformative, creating a kind of cosmic remix where particles, energies, or even fundamental forces combine in ways we can't imagine. Some theories suggest that the universe we live in is not the first or the last, but just one in a series of universes that have been born, expanded, and eventually recollapsed over an infinite timeline. If that's true, then the Great Leap might not be a one-time event, but part of a natural cycle where universes are constantly forming, growing, colliding, and merging. Each collision could seed a new Big Bang, setting off the birth of yet another universe in an eternal chain of creation and destruction. However, detecting evidence of such a cosmic journey is no small task. The distances involved are beyond comprehension, and the effects would be subtle and stretched over billions of years. Researchers studying the CMB and gravitational waves are pushing the boundaries of what we know about the universe's structure. If evidence of these leaks or gravitational pulls were ever found, it would fundamentally change our understanding of the cosmos. The infinite wave. Could space be riding a never-ending ripple? Scientists have long considered space-time to be more than just a passive arena where events happen. Einstein's theory of relativity showed us that space and time can be stretched and warped by massive objects. In this view, the fabric of space-time is somewhat flexible, bending around stars and black holes like a cloth around a heavy ball. But what if, instead of bending only around massive objects, this fabric is also affected by vast slow waves? These waves wouldn't be like ocean waves we see on Earth, with a crest and a trough moving through water. They'd be ripples in space-time itself, so expansive that entire galaxies would ride their subtle slopes, barely noticing the journey. The idea of infinite waves, if proven true, would reshape our understanding of what holds the universe together. If space-time is truly rippling, then the galaxies we see expanding apart may not just be moving outward in a straightforward way. Instead, they could be riding along the crest of an enormous wave, traveling not only through space, but also with it, as space itself shifts in these gentle rhythms. One way to imagine these waves is to think of sound waves traveling through air. Sound is just a series of compressions and rarefactions, causing air particles to move back and forth slightly as the wave passes. But in the case of infinite waves in space-time, there would be no air or particles. These waves would be like vibrations in the very structure of reality, moving through everything with barely any interaction. We might never notice these waves directly because they wouldn't change anything in an obvious way. Instead, they would act in the background, subtly shaping the large-scale motion of the cosmos. If space is indeed moving along a never-ending wave, it could mean that some of the forces we observe, like gravity, are more complicated than we thought. Right now, we view gravity as a force that pulls objects together based on their masses and distances. But if infinite waves exist, they might create regions of space where gravity behaves differently. In the peaks of these cosmic waves, the pull of gravity could be slightly weaker or stronger, shaping how galaxies clump together. Scientists studying galaxy clusters have noticed that some clusters move in directions that don't quite make sense with our current models. These strange motions might be hints of space-time waves. Some theories even suggest that these infinite waves could be responsible for dark energy. Rather than an actual force, dark energy might be an effect of space-time ripples, creating areas where galaxies seem to drift apart. In this view, dark energy wouldn't be a separate component of the universe. Instead, it would be a side effect of the infinite waves, with galaxies riding their crests as they move through the cosmos. The discovery of gravitational waves gave us the first concrete proof that space-time can ripple. But unlike the waves created by black holes, these infinite waves wouldn't be caused by a single event. Instead, they'd be woven into the fabric of space-time itself, always present and always moving, like the steady pulse of the ocean. How would we even detect these vast invisible waves? Scientists are still exploring this question. One possibility is that we might see their effects on galaxy clusters, which move through space at high speeds. If these clusters seem to drift or accelerate in certain directions, it might be due to the influence of infinite waves. Observing how galaxies cluster together or move apart over long periods could provide indirect clues. If these waves exist, they might also explain certain puzzling aspects of quantum mechanics. Quantum mechanics suggests that particles like electrons don't exist in fixed locations, but instead as probability clouds that can spread out over space. If infinite waves are subtly moving everything in the universe, it might help to explain why particles seem to behave more like ripples than solid points. These cosmic waves could act as a kind of background rhythm, influencing the behavior of particles on the tiniest scales. Another intriguing idea is that infinite waves could even allow us to peer into other parts of the universe that we otherwise couldn't reach. If a wave is moving through space-time, it might create a subtle lensing effect, bending light in unexpected ways. This could create strange distortions in distant galaxies, allowing us to catch glimpses of regions of space that are normally hidden. These wave-induced lenses might reveal structures on the other side of the universe, or even provide indirect clues about the shape and size of space-time itself. Stellar orphans, planets and stars, cast out from their clusters. Out in space, not every star or planet remains in the comforting company of its birthplace. Some are cast out, ejected from the familiar clusters where they were born, set adrift in the dark void between stars and galaxies. The presence of these wanderers suggests that the universe is not a serene, orderly place, but a landscape shaped by immense forces, capable of sending even stars and planets hurtling out of the systems that formed them. When a star or planet is ejected, it isn't necessarily an isolated event. The ejection often follows a dramatic sequence of interactions between massive objects in a crowded star cluster. Star clusters, the nurseries of young stars, are dense regions where gravity reigns with a forceful hand. Stars forming in these clusters are subject to complex gravitational forces, pulling and tugging them in different directions. If a star forms close to a much larger star, it could eventually find itself caught in a gravitational tug-of-war. Sometimes, this struggle reaches a tipping point, with smaller stars or planets being flung away at speeds that can carry them clear out of their cluster and into the depths of interstellar space. Once a star or planet becomes an orphan, it enters a new phase of existence. Unlike stars within clusters, which are held in relatively stable orbits, these wanderers become nomads, drifting alone through vast stretches of space. These orphan stars are called rogue stars, and they travel for billions of years. Rogue stars may still shine, but with no nearby stars for context, their light fades into the larger cosmic background. Rogue planets, on the other hand, are dark and nearly invisible. Without a star to orbit, these planets are cold, isolated and hidden, illuminated only by the faint glow of distant stars. Yet interestingly, some scientists believe that these rogue planets might still be capable of harboring life, relying on internal heat or geothermal energy rather than sunlight. These stellar and planetary orphans offer insight into the turbulent past of star clusters and galaxies. By studying their trajectories and speeds, astronomers can trace back to the violent events that cast them out, piecing together the story of their origin. Rogue stars and planets often move at unusually high speeds, a result of the energy they gained during their ejection. These high speeds suggest encounters with massive stars or black holes. It is still an open question how common these ejections might be. If rogue stars and planets are numerous, then the universe may be filled with more solitary wanderers than we had previously imagined. Some estimates suggest there could be as many rogue planets as there are stars in the galaxy, an idea that changes our picture of the cosmos from one of mostly ordered solar systems to one in which free-floating planets drift unseen, occupying the empty spaces between stars. The earliest epochs of the universe were likely even more chaotic than what we observe now. During those early stages, when galaxies were still forming and merging, the gravitational forces at play would have been even more extreme. Collisions between young galaxies would have created environments rich in gravitational interactions, and ejections of stars and planets may have been common. In this sense, the rogue stars and planets we see today could be ancient relics of a time when the universe was still settling into its current form. As we look at them, we might be glimpsing the fossil record of cosmic chaos, with each orphan telling a story of past collisions, close encounters, and gravitational skirmishes. Some of these stellar orphans could even be remnants of entirely lost star clusters or smaller galaxies. If a small galaxy passed close to a larger one, it could experience galactic cannibalism. In these situations, stars that were once part of the smaller galaxy might be cast out, either joining the larger galaxy or drifting into intergalactic space. In recent years, advances in telescope technology have allowed astronomers to detect some of these distant rogue stars and planets. Infrared telescopes in particular can pick up the faint warmth of rogue planets, revealing these cold, distant objects against the backdrop of interstellar space. Even though they're cast away from the clusters that formed them, rogue stars and planets can still affect their surroundings in interesting ways. Rogue stars, for instance, can still form gravitational relationships with other objects they encounter, potentially gathering new companions as they drift. Likewise, rogue planets may still feel the pull of distant stars, or even pass close enough to join a new planetary system, like travelers finding a new home after a long journey. Dark energy beings, speculating on consciousness in pure energy. The universe is filled with mysteries that challenge our understanding of what it means to exist. Dark energy is one of these enigmas. When scientists talk about dark energy, they refer to a force that seems to work against the pull of gravity, spreading everything apart on a cosmic scale. It's as if the universe has an invisible hand, pushing galaxies further from one another. But in a world where we're surrounded by life and intelligence, it's hard not to wonder, could there be more to this vast, unseen force? What if, hidden within the dark energy itself, there are forms of consciousness unlike anything we know? Considering that dark energy makes up around 70% of the universe, it's not a small leap to speculate on the possibility that it holds secrets far beyond what we can currently comprehend. Traditional science paints dark energy as a passive force, a feature of the cosmos that behaves predictably and impersonally. But it's intriguing to imagine that dark energy might be more than a mindless push against matter. What if it possesses awareness or, stranger yet, harbors entities made purely of energy? If dark energy were indeed a home for conscious beings, how would they differ from the life forms we're familiar with? For one, these hypothetical entities would likely lack any kind of physical structure. Unlike us, who are made up of atoms and molecules, beings of pure energy might not rely on anything we would call a body. They could exist as forms of energy patterns, currents, or waves, with nothing solid to anchor them. To them, physical structures might seem strange or even unnecessary, as they would be entirely at one with the fabric of space itself. Communication, if it exists among these energy beings, would be vastly different from what we know. Where we rely on sound waves, light signals, or other forms of sensory input, these entities might communicate through direct fluctuations within dark energy itself. Perhaps they would express thoughts, intentions, or emotions as pulses that ripple across vast distances. These pulses might be so subtle that they blend seamlessly with the natural expansion of the universe, making them nearly impossible for us to detect. To an outside observer, these exchanges might appear as faint variations in the rate of cosmic expansion, barely perceptible and easily dismissed as random noise. If such beings exist in a realm of pure energy, their sense of time and space would be vastly different from ours. Locked into the rhythm of the universe's expansion, they might experience time as a continuous flow without the same beginnings and endings that we do. In fact, time might feel almost non-existent to them, an endless now stretching across eternity. For beings like us, tethered to a linear perception of time, it's difficult to imagine a consciousness without a past or a future. How would a being made purely of dark energy view matter? We might imagine them as perceiving the cosmos in reverse. Where we see stars, planets, and galaxies as dense points of existence, dark energy beings could see matter as scattered interruptions in an otherwise continuous field of energy. To them, the universe might appear as a network of voids around the structures we consider real, with our physical universe resembling islands floating in a vast sea of energy. What we call space would be their reality, while what we consider tangible would be unusual, even exotic. They might view our world of particles and atoms as an anomaly, a curiosity to be observed from afar, much like how we look at distant stars and nebulae. If we push this thought further, we could even imagine that such beings are aware of us in some abstract way, watching as we develop, evolve, and search for answers about the universe. However, given their nature, they might not view us in any traditional sense. we would be as indistinct to them as atoms in a rock are to us, tiny particles in a universe that's dominated by the presence of dark energy. This isn't to say they would lack the ability to comprehend or ponder other forms of existence. Just as we've developed science and philosophy to understand the universe, these beings might have their own systems of thought and interpretation, ways of making sense of phenomena they encounter, like galaxies, stars, and life forms bound to physical bodies. Some theories suggest that dark energy might be a remnant of a previous universe, or an echo from dimensions beyond our own. If this is true, then perhaps these beings, if they exist, are part of a legacy far older than anything we know. They could be the last vestiges of a previous reality, carrying traces of ancient experiences or wisdom. To us, the universe is only about 13.8 billion years old, but to beings of pure energy, time might not be a constraint. It's conceivable that they hold memories or impressions from epochs predating our own cosmic history. Could these entities influence the physical universe? Traditional models suggest that dark energy is merely a force pushing galaxies apart, but if it holds some kind of consciousness, then perhaps these beings could exert influence in subtle ways. We may not see direct interactions, no cosmic hand reaching into our galaxy to move stars, but their very presence might have an impact. For instance, the expansion of the universe might be influenced by shifts in these beings' own existence, changes in their collective awareness or focus. If their thoughts are like waves spreading through dark energy, they could leave ripples that subtly affect space-time, nudging galaxies along different paths, or even altering the formation of structures in ways we don't fully understand. Some speculative physicists have even proposed that dark energy could be the result of information itself, an abstract, non-physical presence that underpins reality. If information can exist without form, then so too might awareness or intelligence. Perhaps dark energy is, at its core, a kind of cosmic consciousness, a field of awareness that permeates everything, a silent observer to the dance of galaxies and stars. In this view, dark energy beings wouldn't be separate entities, but rather part of an all-encompassing awareness, with individual consciousnesses emerging like ripples on the surface of a pond. We're accustomed to the notion that life and consciousness require a physical form, something concrete to hold it. But life might exist as a pure, unanchored awareness, with intelligence spread across the universe like an invisible mist. Strangelet showers. Could alien particles be altering our universe? Strangelets are a type of particles scientists have yet to confirm, but they're thought to be a form of strange matter, named for the presence of strange quarks within them. In our everyday world, atoms are made up of protons and neutrons, which in turn consist of two types of quarks, up quarks and down quarks. Strangelets, however, would contain a third kind, the strange quark, making them fundamentally different from ordinary matter. If they exist, they could introduce properties and interactions we've never seen in nature. What makes strangelets so interesting and concerning is their stability. Unlike regular matter, strange matter could be stable under extreme conditions, holding together more tightly and enduring far longer than anything we encounter in our daily lives. Strangelets, if they're stable enough, might travel through space unaffected by the forces that would normally break down or alter particles. Theoretically, a strangelet could pass right through planets, stars, and even our bodies without being stopped. And while one strangelet might go unnoticed, scientists speculate that a shower of strangelets could cause strange, even dangerous interactions with the matter around us. When strangelets encounter ordinary atomic nuclei, there's a chance they could trigger a transformation. In some scenarios, strangelets might convert regular matter into strange matter upon contact, essentially infecting it with their own unique composition. This transformation is called strange matter conversion, and while it remains hypothetical, if such a process occurred, ordinary matter would lose its familiar structure, replacing its up and down quarks with strange quarks. The idea that strangelets could infect other matter has led some to describe them as a cosmic virus. But unlike biological viruses, strangelets wouldn't spread by replication. Instead, they would alter particles directly on contact. A single strangelet might be enough to set off a chain reaction, turning nearby particles into strange matter, which could then spread further into adjacent particles. In theory, this process could continue indefinitely, potentially transforming entire objects or regions of space. However, for this to happen on a large scale, strangelets would need a level of stability and endurance that scientists have yet to observe, which is part of why they remain hypothetical. One of the questions scientists ponder is how these strangelets, if they exist, might come to be in the first place. One possibility is that they originate in the hearts of neutron stars. Neutron stars are among the densest objects in the universe, with gravity so intense that it compresses matter to a state where protons and electrons merge into neutrons. Under such extreme pressure, quarks can behave in unusual ways, potentially forming strange matter. It's possible that strangelets are fragments of strange matter from neutron stars, ejected during events like neutron star collisions or violent cosmic phenomena that scatter particles across space. If strangelets are indeed remnants of these collisions, they might be scattered throughout the universe, drifting through space like cosmic seeds carrying the potential to alter matter. If strangelets can survive the journey through space, they might eventually reach planets, stars, or even regions like our own galaxy. However, space is vast, and the likelihood of a strangelet making direct contact with a planet or star is slim. Still, in the rare chance that strangelets do enter a planetary atmosphere, they could theoretically alter the chemistry of the elements they encounter. Some scientists speculate that, given the right conditions, strangelets might influence the formation of particles, potentially impacting the evolution of matter on a fundamental level. Even small-scale interactions might lead to anomalies in atomic structure, influencing everything from the way elements bond to the formation of more complex molecules. Could foreign particles like strangelets influence the development of elements in certain regions of space? It's possible that strangelets, by interacting with matter in new ways, might create unfamiliar atomic structures or unusual isotopes that wouldn't otherwise form. In theory, strangelet-induced transformations could result in entirely new kinds of matter with properties we can't yet predict. Events like supernovae or gamma-ray bursts release tremendous amounts of energy, and it's conceivable that strangelets could also form in the heat of such violent events, only to dissipate shortly afterward. If strangelets appear and disappear in this way, they might not have lasting effects on the universe. However, if strangelets can form in space, even temporarily, they might be influencing cosmic chemistry on a micro level. These interactions might be happening all around us, contributing to the complexity of the universe in ways we're only beginning to explore. Particle accelerators, like those at CERN, recreate high-energy collisions that mimic cosmic phenomena, giving researchers a controlled way to study strange quarks and their interactions. While no one has observed a strangelet directly, these experiments offer insights into the conditions that might give rise to such particles. Some scientists are also examining cosmic rays for signs of strangelets. Since cosmic rays travel through space and occasionally strike the Earth's atmosphere, they offer a way to study high-energy particles from distant regions of the universe. If a strangelet were to collide with a cosmic ray detector, it might leave a unique signature, offering clues to its existence and properties. The ultimate end. What if the void itself is destined to collapse? We tend to think of space as a vast, permanent, and infinite stage, stretching out in all directions without end. It's hard to imagine that the very foundation of existence, the fabric of space-time, could come to an end. But some theories suggest that space as we know it may not be eternal. Rather than going on forever, the void itself could one day reach a point where it collapses, and everything that has ever existed might be swept into an ultimate, inescapable end. While there are still countless mysteries about what makes up the cosmos, physicists have identified a few scenarios that could lead to the end of space as we know it. In the universe today, we observe galaxies moving farther and farther apart, as if they are being carried on a river that's flowing faster all the time. Some scientists believe that if dark energy continues to accelerate, it could eventually push galaxies, stars, and even particles of matter so far apart that the bonds holding them together would break. This scenario is sometimes called the Big Rip, a process where space stretches to the point that it can no longer sustain the structures within it. In such a case, matter itself would be torn apart, leaving nothing but a formless, inescapable void. Another theory, known as vacuum decay, imagines a slightly different fate. In this scenario, the vacuum of space, the so-called empty background that all matter exists within, might not be as stable as it appears. According to quantum mechanics, particles and fields are never truly at rest. They fluctuate, even in what we think of as empty space. These fluctuations might hint that the vacuum we experience is just a temporary state, like a surface layer on a much larger, more complex structure. If there were an even lower energy state of the vacuum, it's theoretically possible that the universe could tunnel into this lower energy state, triggering a vacuum decay. If vacuum decay were to occur, it would happen almost instantly. A new bubble of space with different physical properties would form and begin expanding at nearly the speed of light, consuming everything in its path. This bubble would erase the known laws of physics, creating an environment hostile to all forms of matter as we know them. It's often said that this process would be silent and instantaneous. No one would see it coming. The entire universe would be swept away in a cascade of destruction, as the void itself restructured into something completely foreign, something unimaginable. This wouldn't just affect matter, but the very rules that allow matter to exist, leading to an absolute end for everything we know. There's also the concept of a big crunch, a theory suggesting that rather than expanding forever, the universe could reverse direction and start contracting. In this scenario, the gravitational pull of matter would eventually overpower the outward push of dark energy. As galaxies, stars, and planets begin moving closer together, they would ultimately converge, crushing everything into an unimaginably dense state. While this idea has fallen out of favor, due to recent observations indicating that the universe's expansion is accelerating, it remains a possibility in the grand list of cosmic endgames. Some scientists speculate that if a big crunch were to occur, it might lead to another Big Bang. This would mean that the end of one universe could give birth to another, creating a cycle of cosmic death and rebirth. However, if dark energy continues to drive the universe's expansion, a big crunch might never happen, leaving open the question of how, if ever, the universe might end. One idea about the ultimate end of the void involves something called the heat death of the universe, or the Big Freeze. In this scenario, the universe continues to expand indefinitely, but over time, stars burn out, galaxies drift apart, and black holes slowly evaporate. Energy disperses, and temperatures drop close to absolute zero. Without stars or active processes, all motion would eventually cease, leaving a vast frozen expanse. This is sometimes called the entropic end of the universe, where everything reaches maximum disorder and the cosmos becomes a cold, dark wasteland. In this outcome, space wouldn't collapse, but would instead become a barren, silent void, devoid of any life or activity. Some scientists wonder if the end might involve a form of collapse that is neither a big crunch nor a big freeze, but something stranger, a shift where space itself becomes unstable, triggering a universal collapse that doesn't require gravity or entropy to wind things down. Instead, this shift might be the result of an unknown process that alters the fundamental structure of the universe in an instant. In this hypothetical collapse, the fabric of space might change so drastically that all particles and forces simply dissolve, leaving only a kind of pure, formless void. No stars, no galaxies, no particles, just an endless sea of nothingness. The void we see as empty now might be vastly different from this final void, which would lack even the most basic fields and energies that define the present universe. What would it mean for consciousness, for memories, for everything ever achieved or experienced? If such a collapse were to happen, it would erase everything instantaneously. There would be no traces, no ruins, and no remnants. It would be an ultimate silence, a complete and total end. This vision of collapse is not a comforting one. It offers no continuation, no cycle of rebirth, no way to preserve even a whisper of existence. It's a scenario where not only space and time end, but the very possibility of existence itself disappears. And on that existential note, this journey comes to an end. Comment your favorite wild fact about the universe that I missed. If you enjoyed the video, consider leaving a like and subscribing to the channel. Thanks for watching.